Hi everyone. So today we're going to start on 5.2, derivative of several function of several variables. So in this chapter, we are actually going to finally define what would be derivative of a function. So recall from last chapter, we actually did not really learn about derivative of any function that have several variables yet. We learned what we call partial derivative, but that's, as I mentioned, is not really derivative. So in a quick recap, let's just talk about what we have known so far. So in 4.3, we learned that when we're given a function f that map from Rn to R, f is a real value function of several variables. Oops. The way it works is that the function would most likely look something like this: is f of vector x equal to y, where vector x is equal to x1, x2, to xn. So there are n variable that just basically referred to as x, but with different subscripts, and the output is one single variable, which is y. And we learned that the graph of f is basically the set of points that look like this: x1, x2, to xn, and then we can put in the y variable together. And because of that, this are the independent variables. There are n of them. And then you have one extra dependent variable. And that combined together to form the graph. And so therefore we learned that the graph, its graph is an n-dimensional surface in Rn plus 1. Because it's n-dimensional, because they're n-independent variable, but the output actually have an extra dependent variable that we have to put in, and therefore become n plus r to n plus 1. So those are what we learned in 4.2, technically speaking. In 4.3, we learned about partial derivative. We learned that f has n partial derivatives, mainly one for each of its independent variable. And these partial derivatives are probably something like this: df over dx1, df over dx2, to df over dxn. And remember, we do have this little scripted d to indicate partial derivative. And interesting thing about a partial derivative is that the partial derivative actually is the same type of function as f. So each of these partial df over dx sub k would be a function that maps from Rn to R. Okay, and we also learned that each of these partial derivative and partial derivatives are basically slopes of the tangent to the coordinate curve. And as a matter of fact, this slope will represent the following: df over dx sub k basically represent the ratio of f changes, or f, maybe I should write this, df over dx sub k represent the ratio of change in f over change in x sub k. So these are pretty much everything that we know so far about several variable function. So now we're ready to actually make the jump and say, well, what if we want to find the derivative of this type of function? What would the derivative be? Well, we know this thing called partial derivative, part of the derivative. But how does that play into the quote-unquote derivative of the function? So try to understand that. We're going to try to go back and try to think about what is derivative based on what you have learned from BC calculus. So from BC calculus, you probably remember learning the following concept. One of the most important concepts in BC calculus is that we define derivative of f to be slope of the tangent, and we approximate the slope of the tangent by using the slope of the secant. So in BC calculus, we defined derivatives to be basically slopes of the tangent, and we can approximate the slope of the tangent using slope of the secant. So how does this work? Well, I'll show you, and I'm sure you probably remember seeing this picture before. So imagine that I have a graph, and I'm just going to focus mainly on the first quadrant, just so to make my graph look nice. And let's say I have this graph right here, which have some kind of parabola curve or something. So y equal to f of x. Let's say I want to find this value, which is f prime at x sub 0. I'm going to define somewhere over here is x sub 0. So then this point is basically x sub 0, f of x sub 0. I'm going to try to find f prime at that point, meaning I'm trying to find the slope of the tangent at that point. But of course, here comes the problem. The problem is that in order to find slope, I technically need 2 points, but I only have 1. So how are we going to approach this? So the way I approach this is the following. Is to define a second point in the graph, which we're going to call this point right here, which is x, f of x. So this point is completely changeable based on what x is. And I'm going to define a line that goes through these 2 points. This line is what we call the secant line. And this secant line now have a slope. Okay, and that slope will be following. So if let me try to do this first. So this is what we try to figure out. So the way to do that is to first define, okay, well, we have this thing called the slope of the secant. So MSEC, that's secant stand for. Well, that would actually equal to f of x minus f of x sub 0. So that's change in y over change in x. And notice that this slope of the secant is actually the function based on where we put x. So what we want to do is to take x and move it toward x sub 0. And that would mean that our x value would move closer to x sub 0. Then this point will move along the curve and closer to x sub 0, f of x sub 0. And when we do that, eventually these 2 points become 1 point. And now I will have a line that's formed by 1 point, and that's basically what the tangent would be. So therefore, the simple concept is that f prime of x sub 0 is basically equal to slope of the tangent, which is basically equal to limit as x approaches x sub 0, the slope of the secant. And actually, you know what? We'll just call it MTAN. So that was tangent. All right. So that's what we define f prime to be. F prime of x sub 0 would actually equal to limit x approaches x sub 0, f of x minus f of x sub 0 over x minus x sub 0. So this definition right here, this expression, it gives the slope of the tangent for the function f of x at the point x sub 0, at x equal to x sub 0. So that's actually give us a definition of the derivative at a given point x sub 0, which can be formed by using the slope of the secant and then take the limit of that. Notice that this formula is slightly different than the definition of the derivative, and as a matter of fact, I am actually trying to define derivative slightly different in a way that we'll be able to use for function that have that's a several variable. So now, interesting thing to note is the following: this expression actually can be manipulated, and it can be manipulated into something a little different. So what I'm going to do is the following: I'm going to try to manipulate this expression and show you a different way to look at this expression. And then I can then define something called differentiability. Basically what you learn in BC calculus, but with a different definition. So what I'm going to try to do is the following. Let's say assume that this is what I have. What I'm going to do is I'm going to take this expression. I'm going to move f prime, okay, to the other side and see what happens. So therefore, if I do that, I actually have limit x approaches x sub 0, f of x minus f of x sub 0 over x minus x sub 0 minus f prime of x sub 0 equal to 0. So I simply move f prime of x sub 0 to the other side. And then what I'm going to do is I'm going to combine them into one single fraction. And when I do that, I have this expression. Now, hopefully some of you start to recognize something that's interesting here. And the interesting part is actually this part right here. What I'm going to do, I'm going to factor out a -1. And when I do that, I have this expression. Limit as x approaches x sub 0, f of x minus f of x sub 0 plus f prime of x sub 0, x minus x sub 0, all over x minus x sub 0 is equal to 0. And hopefully some of you probably recognize this little part right here. And if you do, good for you, because that means that you have been paying attention and you did something that I asked you to do for like 3, 4, 5 times already, is to write out the tangent formulas for all the different tangent formulas that you know. Because in this expression right here, this little part is actually the tangent line at x sub 0. So therefore, this entire expression basically identified the following. It basically identified the fact that when x approaches x sub 0, in order for this limit to equal to 0, this top part must equal to 0. And therefore, this definition basically saying the following, is that a function have its derivative when you have this little slope that can form this tangent line where the function is actually equal to it. A concept that you learn in BC calculus called local linearization, which basically is saying that any function that's differentiable must have some kind of tangent at that point. And that tangent is formed by some kind of expression that involves this little thing called the slope. With that being said, now I can define a kind of new concept of what we call derivative, using what we just using this expression right here. So remember, this expression basically saying that the function f and its tangent become almost the same as x approaches x sub 0. How do I know they become the same? Because when I subtract these two things together, I get 0 from it. And only way when you subtract two things and get 0 is when they're equal to each other. So therefore, this expression basically implies, now maybe I should write that down first before I do this. So therefore, this expression this expression equals 0 implies f of x minus f of x sub 0 plus f prime of x sub 0, x minus x sub 0, to be equal to 0. Now, you might be thinking, why does that imply that? Because of the following. If I look at the expression, if x does approach x sub 0, what does that make the denominator? Well, notice the denominator is x minus x sub 0, so when x becomes x sub 0, then the denominator would become 0. And whenever you have something that's divided by 0, it does not exist. But the limit could exist if it ends up having an indeterminate form. And that indeterminate form that we're looking for, 0 over 0. So therefore, this expression equal to 0 implies that it must become an indeterminate form when x approaches x sub 0. And so, therefore, forces the numerator to have to be 0 also for it to become indeterminate. And therefore, turn into this expression. Therefore, imply that the function f and its tangent, remember that's the tangent at x sub 0, must become almost identical as x get closer to x sub 0. And that is essentially the essence of what the derivative of the function is, because the derivative play a major part in forming that tangent. So now, maybe now we can define something that you probably remember learning last year called differentiability. Let's say given a function f that maps from R to R. And let's say f is, so we go define the term, okay. Let's say given f map from R to R. Let's say f is differentiable, so I'm going to defining this term differentiable. Is differentiable at x sub 0 if there is a scalar, which we're going to call f prime at x sub 0, such that the following limit is true. And that limit, of course, is this one right here. Limit as x approaches x sub 0, f of x minus f of x sub 0 plus f prime at x sub 0, x minus x sub 0 over x minus x sub 0 is equal to 0. And this little value right here, f prime of x, f prime of x of 0, is called the derivative of f at x sub 0. So therefore, there's this unique number, which basically is the slope, that allow us to form this tangent vector, or this tangent line, that would make it to be the same as f of x as x approaches f0. That's essentially what the derivative does. So therefore, which is the reason why last year in BC Calculus, as well as this year, every time when we learn something about derivative, we always talk about tangent, because they are they're not identical, definitely, but they are related in such a way that they are almost one follow the other. Now, why do we go through all this? Because you already learned about differentiability. And differentiability meaning that when you f prime of x sub f prime x sub 0 exists, then therefore the function would be differentiable at x sub 0. So here I'm basically defining differentiability is that value must exist, and not only that it must exist, but it also must be the right value, meaning the value that will form the tangent line in this case. Now comes the next question. How do we generalize this concept to a vector, to a several variable function? And that's what we want to do. So the way to do that is actually pretty easy. So let me show you the definition. So now what happened is, the big question is, how can we use this definition on functions with several independent variable, basically function f that map from Rn to R. Okay, yes, we still go focus on just single dependent variable, real value function. But what if we have multiple independent variable? How does that work? So I'll show you how that works. The concept actually very simple. So give you the definition. I will show you the expression. So our definition actually will define pretty much the same way as this definition right here, except we're going to talk about Rn to R. So show you definition. So let's say given f map from Rn to R. I'm going to try to mirror the definition to be this one right here. So we're going to say f is differentiable at x sub 0. But now remember, because our function f here is from Rn to R, therefore its domain or its input actually has to be a vector. So I'm going to put down an arrow to indicate it's a vector. F is differentiable at x sub 0 if, let me see how I write this, if there is a scalar, and I'm not going to name this scalar, so I'm going to call this something different. I'm going to call that k, such that, and actually what I'm going to do is I'm going to have to amend some of this, so I'm going to leave some room. I'm going to leave room right here, so please leave some room, such that the following limit is true. So notice that this definition basically say the same thing as the other one, except I'm changing the function. And so I'm going to put down the limit exactly the way it is. So limit x approaches x sub 0, f of x minus parenthesis f of x sub 0 plus f prime, or well actually I'm going to not call it f prime, that's what I'm going to define, k times x minus x sub 0, yes, I'm leaving a little bit of room, over x minus x sub 0 is equal to 0. Now, obviously this expression doesn't work because it doesn't account for the fact that input is a vector. So how about we fix that right now? So notice that this function f take in a vector, so therefore the input is not just x but vector x. And we established that at x sub 0, that x sub 0 has to be a vector, so I'm going to go and put that as a vector also. Okay? And now become issues. Why is an issue? Because the following. If I look at this expression right now, notice that f of x, this thing, as well as this thing, both of these are referred to the output of the function, which in this case, the function map into a single scalar. So therefore, these two things are both scalars. But here comes the problem. What is this thing right here? This is actually a vector in Rn. So now comes the problem. The problem is that I have a plus sign right here. May I have to somehow combine this scalar, which is f of x sub 0, with this vector. But there's no such operation. We don't know how to add a scalar with a vector. So how do we solve that problem? So the way to solve the problem is the following. Is to define our k to be a vector also and allow us to perform a dot product, because a dot product between a vector and a vector become a scalar that would then allow us to actually define f of x sub 0 plus that scalar. So therefore, I'm going to have to amend my statement. It's actually f is differentiable if we have a vector k in Rn such that this limit is true. That's almost good, but not good enough yet. The reason why it's not good enough, because if I look at the bottom right here, this is also a vector in Rn. And we actually don't know an operation that will allow us to divide a vector. But if you think about it, the essential idea of x minus x sub 0 is basically talk about the difference between them. And another word for difference in geometry is distance. And so if that means distance, then I can actually fix that problem by doing this. So now this whole thing now become a length, which is a scalar. So now with this being absolute value, now this thing become a scalar because it's length, and these two things combined become scalar. So now the numerator basically become a scalar minus a scalar plus another scalar, so it's a scalar, over a scalar on the bottom. And so now we have that equal to 0, which is a scalar. So this definition define what is differentiable, is that our derivative is actually have to be a vector, not a scalar, in case of a function with several variables. That is extremely important to understand. So in this scenario right here, is this definition, vector k, if vector k exists, then it is called the derivative of f at vector x sub 0. It's called the derivative. Now, generically, we do refer to this vector k as the derivative, but it actually has a special name. And the reason why there is a special name, because it actually doesn't do what we think derivatives should do. And I'll explain more to you later, so obviously don't worry about it if you don't understand right now. But this derivative actually has a name. We actually call this, this. K is actually called the gradient vector of f at x sub 0. And its notation the notation for gradient is this upside down delta of f. All right, now I know that we passed the 30-minute mark, so I'm just going to mention one last thing and that's it. So note, important to understand is the following. Let's say given a function f that met from Rn to R, this is what we know. Gradient of f, okay, so maybe I would say that f of vector x equal to y. So that's how a function looks like. The input is vector x. This gradient, that's upside down delta of x, which is a variable, is often referred to as the gradient vector function. However, we most likely refer to it as just gradient. Okay, or sometimes maybe I just call it gradient function. If you have gradient of f at x sub 0, then that usually referred to as the gradient vector at x sub 0. And probably one of the most important things that I want to point out about gradient, that was the last thing I'm going to talk to you about, is the following. If the function f met from Rn to R, then gradient of f actually met from Rn to Rn. Now, why is that? Because if you think about it, we already established that this vector that fit into a definition has to be a vector in Rn. So therefore, when you define the gradient, it requires the input to be vector x, which is in Rn, and it must give out a vector that also in Rn. So that's extremely important, because notice that this is different than what we have learned so far about derivative. Because if you think about it, all the derivative we have learned so far actually kind of maintain the dimension. It kind of have this closure property. Okay? Think about tangent, standard tangent vector, which is velocity vector, and acceleration vector. Think about higher order partial derivative. See, all of them have closure property, but this one does not, which is one of the reasons why we gave it a different name. We actually rarely call this derivative, but instead we'll use the word gradient more often because of the fact that it's very different compared to what we perceive to be derivative. Unfortunately, my time is up, so I guess we will continue this on our next video. All right? Talk to you guys later. Bye-bye.